Hi there, my name is Christopher Worse and welcome to the video or the playlist, the first video of Homework 5, which is going over the adiabatic flame temperature. This is for part 1, which asks us to explain how the moles of each species in the feed and product flame are determined from the reaction stoichiometry and given excess of air in a scenario where natural gas comprising 95 mole percent methane, 4 mole percent ethane, and 1 mole percent propane burns with 20% excess air. So overall, we're going to be calculating the adiabatic flame temperature. So first and foremost, I'm going to pull up the methane, ethane, and propane formulas. So we have methane as CH4, ethane as C2H6, 2 carbons, 6 hydrogens, and then propane has 3 carbons, 8 hydrogens. So, with that pulled up, and I can get rid of those, I can move on to drawing out the situation and then figuring out the stoichiometry with, in general, and then with a given excess of air. So let's start by drawing out the actual situation. So we have a burner, call it a Bunsen burner, a flame of some sort. It's adiabatic, which means no heat is lost in the reaction or in the build, so that every amount of energy going in is the same amount as energy going out. So no heat lost there. Now, what's coming in is two things: a mix of the fuel, which is the methane, ethane, and propane, the natural gas, and air. So we have two things coming in. Again, our fuel and air. And now we already have our mixture of fuel, but what's air? Because we need it for stoichiometry. So air is 21% oxygen, 79% nitrogen. So with that, we can now calculate the stoichiometry because we're doing combustion reaction. So combustion reaction is we take our fuel, we add oxygen, it burns, and then it gives us carbon dioxide and water. So we have all our fuel plus our oxygen. And they all go to CO2 and water. So let me swap sides. Erase it real quick. All right. So we have our general combustion reaction system, our stoichiometry. Now we just need to put in moles, but if you noticed, there are spaces there. Specifically a space here, and there's a bunch of space on the all the way to the right. We have our nitrogen. So the nitrogen isn't doing anything, but it needs to be represented. So all of these are going to have nitrogen in them. Now how much? Well, if it's 79%, that means that there is 79 over 21% of oxygen amount of nitrogen, because that's how much percentage it is. So 79 over 21, and I'll add that to everything. Okay, now we have that. Now we can add the moles. Of course, this nitrogen also goes over to the other side because it's not used in the reaction. So 79 over 21. Nitrogen, 79 over 21. Again, nitrogen. There. Now we have all of our represented molecules, and now we can get to the stoichiometry. So we'll start with the number of carbons and the number of carbon dioxide atoms. So you notice that there's only one carbon in the methane. So there's one carbon in CO2. So we're good there. We don't have to adjust either of these two. So now all that we have to worry about is the oxygen. So we have two oxygens, and we also have to worry about our hydrogens. So we have 4 hydrogens coming in. We have 2 hydrogens per H2O molecule. That means that there is 2 moles of water per mole of methane. So now that we have all of that set up, we can count our moles of oxygen. So 2 times 1, 4. That means that we have 4 moles of oxygen in this reaction per mole of methane. And then because this is 79 over 21 nitrogen is equal to the amount of oxygen, we also have 4 moles of that. Now that's going to be running case throughout. That O2, the amount of O2 is the amount of oxygen and nitrogen is the same, or at least represented the same. So let's move on to the ethane, C2H6. So 2 carbons, which means that there is 2 carbon dioxide atoms. 6 hydrogens, which means that there are 3 moles of water. And that means that we have some amount of oxygen. So we have 2 times 2, 4, plus 3, 7. Oops, almost forgot. This is not 4, but this is 2. Because this is multiplied by 2. So we have 2 times 2 is 4. 2 plus 2 times 1 is 4. So now we're there. So we have 4, 7. This means that this must be 7 halves. Because again, 2 atoms of molecule, 2 atoms of oxygen in an oxygen molecule. So that also means that there is 7 halves of that nitrogen there as well. 7 halves moles nitrogen represented. Finally, let's move on to the propane. We've got 7 halves, or not 7 halves, 3 carbons, so 3 carbon dioxide. We have 8 hydrogens, so 4 waters. That means that we have 6, 10 divided by 2, 5 moles of oxygen, as well as, because they're equal or equivalent, 5 moles of that nitrogen, or 5 times the fraction times nitrogen. So we have that, and that's our stoichiometry. That is the reaction for this adiabatic flame temperature. But it asks us specifically, given excess of air. Now, given excess of air means that there is more air coming in than is necessary to complete the reaction. That means that there is going to be a product of air coming out. It's going to be hot air, but it's air nonetheless. So with 20%, again, 20 in percentage is just, or 120% is just 1.2. So I'm going to multiply the oxygen and the nitrogen on the left side by 1.2. And I'll erase these to give more room. So again, all of these are going to be added by, multiplied by 1.2, multiplied by 1.2, and then multiplied by 1.2. So I have that there. Now, how does this affect this side? Because it must affect this side somehow. So this, everything but 20% of oxygen is going to be used up, which means that that 20% of oxygen has to be left over. So now, there's a new product, which is 0.2 times the oxygen. In this case, it's 2 moles of oxygen. Another 0.2 times, this is 7 halves. And then 0.2, that's 5 moles. So we have that. And then, same thing here. This is going to be multiplied by 1.2. So I'm going to erase these here very slowly, and simply go write it smaller. 1.2 times 2. I apologize if that's crowded. Running out of room. We've got 1.2 or 6/5. Might actually be easier to do. 6/5 times 2. Yeah, that's better. Takes up less space. 6/5 times 7 halves. And finally, 6/5 times 5. Or, funnily enough, that cancels out to just 6. So now that we have that, we have our stoichiometry, and we can use that later to figure out what we need to do in our coding to finally figure out at the very end the adiabatic flame temperature. Thank you very much for watching. The next video will go over parts 2 and 3 because they kind of meld together. Hope you have a great day.